If you remember in the last video, we introduced summation notation, which by the way is also called sigma notation. I should point that out to you. And so, again, I told you that this symbol was the Greek letter, capital letter sigma, the uppercase sigma in the Greek alphabet. And we saw that if we had a constant times a factor in each term of a summation, we could take that out in front of the summation. Summation was the sum of a sum. We could sum the expression separately and then add the results together, and the same is true of differences. We saw one more thing, that if I sum, all right, from as k goes from 1 to n, k raised to the 0 power, or um, or 1 together as k goes from 1 to n, that summation was worth n. So, I mean, maybe a couple of examples would be helpful here. So the sum as k goes from 1 to 20 of 1 is 20. The sum as k goes from 1 to 700 of 1 is 700, and the sum as k goes from, I could also write this as j. I could use anything I want for this index. J goes from 1 to 100 of 1 is 100. So we have that sum. Now I wrote it this way because I wanted you to see that this follows in a pattern here. What we're going to do is now we're going to develop a sum for k raised to the first power. And so we have this sum as k goes from 1 to n of k to the 0 is n. All right, now what I want to do is I want to look at the sum as k goes from 1 to n of k, which would be 1 plus 2 plus 3 all the way out to n. Now, so for example, the sum as k goes from 1 to 3 of k is 1 plus 2 plus 3, and that would be 6, and so on. But notice it would be a much bigger job if we had the sum as k goes from 1 to 30 of k. All right. So what we'd like to do is we'd like to develop a formula for that. And so notice that this is k to the first. And so to do this, and there's another way that you could look at this, and it's done in your text. So look at your text. But this develops a pattern where we could keep on building on this. Let's compute the sum as k goes from 1 to n of this expression, k plus 1 squared minus k squared. Notice we're trying to develop a formula for as the sum goes from sum of k going from 1 to n of k to the first. And notice these things are both being squared. This is what's called a telescoping series, and let me show you why that's true. Let's write out a few terms of this. When k is equal to 1, k plus 1 will be 2. This will be 2 squared minus k is 1 squared. Of course, 4 minus 1. And we could combine those, but it's more helpful to look at it like this. When k is equal to 2, this will be 3. So we'll have 3 squared minus k is 2 squared. When k is equal to 3, we'll have 4 squared minus 3 squared. And when we can keep on going like this till finally we get to the end. When k is equal to n, we'll have n plus 1 squared minus n squared. And now why is this called a telescoping series? Now look at what happens here. Look at what happens here. If we look at this, notice when I combine these two first expressions together, I'll have a 2 squared, but then I'll be, in this next expression, I'll be subtracting a 2 squared. Notice the first, in this case, it's the first term of the predecessor term of the summation, and minus the second term of the subsequent term of the predecessor, and those subtract off. And then the first term of the first one second term of second one, those subtract off. And can you see that if I would have written it in, I didn't, but there would be in the next term, the first one that doesn't appear here, there would be a 5 squared minus 4 squared, so the 4 squareds would subtract off with what's here. And by the way, if I look at this, this negative n squared would have subtracted off with stuff in the previous term. And so this is why this is called a telescoping series. We have all these terms, but they just sort of collapse into basically this result. Negative 1 squared plus n plus 1 squared. And that's it. So these are pretty easy to evaluate, evaluate, because now if n were 100, well, this would be negative 1 plus 100 and 1 squared. Okay, so that we could do that pretty easily. So anyway, let's simplify this a little bit. This is negative 1 plus, if I multiply this out, I'll have n squared plus 2n plus 1, and notice now these 1's subtract off, and so I'm just left with n squared plus 2n. N squared plus 2n. So that's what this sum is worth. So I calculated it one way using the fact that it was a telescoping sum. All right, now let's take a look at this, and let's look at this another way. Okay, using those linear properties that we just developed up above, that we could take out constant factors and we could split summations up into their separate terms and so forth. But let's look at this. If this is going to be the same thing as the sum as k goes from 1 to n of, well, this expression, if I square it, it's going to be k squared, right, plus 2k plus 1, all right, and I'll be subtracting k squared. So of course the k squareds subtract off, and I'm simply left with this sum as k goes from 1 to n of 2k plus 1. And notice what that would be. That would be splitting these up into two separate terms, taking out the constant factor. This is going to be 2 times the sum as k goes from 1 to n of k plus the sum as k goes from 1 to n of 1. Now this one we developed a formula for. We're just adding 1 together n times. So this is just 1. So we'll have 2 times the sum as k goes from 1 to n of k plus n. Okay, we developed that formula. So now we have 2 ways of looking at this. We remember using the idea that this was a telescoping series. This sum became, I should say, a telescoping summation. A series is when it goes on forever, but this is telescoping summation, and we got that this summation was equal to n squared plus 2n. Now using these linear properties, we got it that it was 2 times the sum as k goes from 1 to n of k plus n. Remember, we were looking for the sum as k goes from 1 to n of k. That appears right here. So we should be able to solve it. We have 2 expressions that are the same. Now remember that we had 2 ways of computing this summation as k goes from 1 to n of k plus 1 squared minus k squared. All right, one method gave us the result n squared plus 2n. The other one gave us the result 2 times the sum as k goes from 1 to n of k plus n. And so what I could do with this is I can just solve it for this summation. So I'll subtract n from both sides. And I'll get, that will lead me to n squared plus n is equal to 2 times the sum as k goes from 1 to n of k. And then I could divide both sides by 2. The 2's will cancel on the right, and we'll be left with the sum as k goes from 1 to n of k is equal to, this is usually people factor this, and so this is written as n times n plus 1, all divided by 2. So I have that formula. Okay, and so let's take a look here. I will skip over calculating this next formula. Let's take a look at an example. I believe I have an example at the bottom here for us to look at, us to try. And that's, oops, I guess we can't do that. Let me make up an example. All right, and the example might be this. All right, let's suppose that we want to evaluate the sum as k goes from 1 to 100 of, let's see, 2k plus 3. Well, that would be, using our linear properties, 2 times the sum as k goes from 1 to 100, plus, we could think of this as 3 times 1, so plus 3 times the sum as k goes from 1 to 100 of 1. Oh, I'm sorry, this first one was of k. And this will be 2 times, well, in this case, the sum as k goes from 1 to n of k is n times n plus 1. So n here is 100. We'll have 100 times 101 all over 2 plus 3 times, remember the sum is k goes from 1 to n of 1 is n. Here the n is 100, 3 times 100. And so this is going to be, well, the 2's will cancel. I'll have 100 times 101, so that would be 10100 plus 300, and that's going to be 10400. And so that would be my sum. Notice we don't have to add up all those terms. It's pretty easy to do. Just apply those formulas.